We are the Oregon State University Mars Rover team. For the past 7 months, we have been researching, designing, and building the next generation Mars Rover ready to compete in URC 2018. Our team is split into 4 sub-teams: mechanical, electrical, software, and science, but all work together to create a powerful, intelligent robot. Learning from our successes and failures from last year's competition, we have made dramatic improvements to all aspects of our rover's design.
We are largely reusing our competition-proven chassis from last year. It retains the 6 independently driven wheels with balloon tires and a simple triple bogie suspension system that enabled us to successfully navigate the variety of terrains encountered during the competition tasks. Our custom Protocase e-box has been designed to fit all our electronics in a compact space, saving weight and leaving more room for the arm and navigation tower. The navigation tower consists of our radio and main camera pan-tilt assembly. Our Ubiquity radio attaches to the main mast with sheet metal and Teflon brackets to reduce weight and radio interference. The main camera pan-tilt is elevated to allow a wide field of view. We are also including an additional 2 cameras on the rover, one on a pan-tilt at the front of the chassis and another at the rear with a view of the undercarriage. These will give us an unimpeded view of the rover and its surroundings. While we still have a fully functional backup arm from last year, we decided that a significant redesign was necessary to excel at competition. Our new arm contains over 60 custom CNC machine parts and has 6 degrees of freedom that allow it to contort to many otherwise unreachable positions, saving us valuable time and giving us greater flexibility. 4 of the arm joints have harmonic drive gearboxes, which will have minimal backlash, high torque, and extreme accuracy. Absolute encoders at each joint give us precise feedback on the orientation of the arm at all times. Having learned the importance of fine control on rover-to-operator communication from last year, we designed our new end effector with 3 under-actuated fingers, as well as force and position feedback. Our end effector has a wide grasping range for manipulating heavy tools or containers in the extreme retrieval and delivery task, while still providing fine control to adjust knobs and switches for equipment servicing. With a wide-angle camera embedded in the palm of the gripper, we will have a direct line of sight to the objects we interact with.
For the first time in our team's URC history, Rover software now runs on Robot Operating System. This move reflects the need for complex autonomous decision-making and also works harmoniously with the decentralized nature of this year's electrical systems. We're using an NVIDIA Jetson to host the ROS framework. This high-performance computer gives us the ability to run multiple cameras and transfer high-bandwidth data to our ground station while maintaining a small physical footprint and long battery life. Communication with hardware on the rover is primarily being done over Modbus using 485. Modbus ensures more reliable communication to hardware nodes on the rover with a proven industrial standard. An important addition this year is the Z Stereo Vision camera system, which will supplement our GPS and IMU with obstacle avoidance data during the autonomous phase of competition. Our custom ground station software will display multiple rover video feeds, mapping data, arm joint positions, rover heading, system statuses, and autonomy controls on 2 monitors while also transmitting drive, arm, and camera control data back to the rover.
This year, we have implemented a decentralized electronics system that moves much of the complicated circuitry out of our main electronics box into a network of interconnected nodes spread across the rover. This custom network allows for seamless replacement of broken nodes in the field, keeping us running throughout the competition. Our communication system utilizes the Ubiquity Rocket M2 radio for high bandwidth, reliable communication. We have tested the Ubiquity radios locally beyond the ranges that we expect during the URC competition, and they've performed extremely well. In order to increase the reliability of our drive system, we have designed our own custom motor drivers that have a lot of overhead built in to prevent failures. We improved our supply chain by purchasing components from more reliable vendors, which will increase dependability of the systems in our rover. We are reusing our robust 6-cell LiPo battery from last year, as it provided sufficient power for an entire day of competition.
To address the scientific challenge, the rover will be equipped with a shrouded auger to retrieve soil samples, several onboard probes, and an automated sterile sample containment device. The soil probe will measure soil temperature, salinity, and water content, both on surface and subterranean soil. A dust sensor will also be used on the rover to evaluate field conditions. High dust content in an environment poses a risk to rover functionality over a long mission. For the laboratory portion of this challenge, 2 tests are planned. The first will use anhydrous spray to test for the presence of amino acids in the soil. The anhydrous organic molecule reacts with amino acids to form a purple dye, which is easily visible in the soil sample. The second type of test that will be utilized is a garden variety soil test. This will give an estimate of how much nitrogen and phosphorus is present in the soil, as well as the pH.
Thank you for considering us for this year's URC. We can't wait to see you in Utah.